Yeah, so this is the second lecture by Javier on symplectic geometry at null infinity. You have 50 minutes plus 10 for questions.
Okay, okay, great. Welcome everybody again. I want to start by asking you if you have any questions regarding yesterday. Okay, so if there are no questions, yesterday at the end we kind of arrived at the example for young meals, which kind of quickly we arrive at the radiated fall-offs, how they form this radiated phase space, and also the construction of the symplectic form for the radiated fields. And the idea here was that the main idea is that if we think of electromagnetism, for example, electromagnetisms, and this is part of the questions that were asked yesterday. So if we think of electromagnetism, we want non-vanishing radiation reaching scribe class. So that means that the Poynting vector in electromagnetism will be non-zero in scribe class. So if we have a non-vanishing Poynting vector, that means that we can translate that condition into a component of the electromagnetic tensor. And that is the starting point for the fall-off condition. So we want, for example, the component UA, which means that this is the transversal component for the spheres, but in the direction U. This guy will be order 1 when we go to R with R to infinity. So we can translate this fall-off in F to fall-off in A, and therefore, what it was written here, and therefore we can have some fall-off in terms of the vector potential AA. The same goes for young meals, okay? And the same we can say about the limits when we go to U minus infinity and U plus infinity. We have to say something about the fall-offs in U in that case. Once we have all this, we can write the symplectic form, just like a limit, just taking the Cauchy surface and pushing the Cauchy surface all the way to scribe plus. And in that way, we arrive at this expression. So I want to start today with the example of gravity, because that example will allow us to discuss what happens when we want to relax the boundary conditions a little bit, and how to treat that relaxation in terms of the phase space, and how to extend the phase space so that we include this relaxation of the boundary conditions. Okay, so let's start with gravity. We consider Bondi gauge. Okay, Bondi gauge is related to this gauge in gravity that allow us to study radiation at null infinity. So let me put this draw that I have here. Okay, so we have some space-time here that it contains matter in some compact sets. Okay, so this is a Cauchy surface at T1. It contains compact set within which is the matter content of the space-time, and the same goes for sigma T2. So if we have some inward radiation, these green lines, it will interact. Okay, so all this radiation will interact with the matter content of the theory, and then will be scattered to scribe plus. So it comes from null infinity, from past null infinity to future null infinity. And some observers in here will read all the radiation that it's incoming to them. And the way that Bondi gauge works is that one can define first the null coordinate U. One can assume that we have a foliation in terms of U for the space-time. Then we define the radial coordinate, which is usually called the luminosity coordinate. Okay, this is one can see really nice construction of Bondi gauge in the papers by Barnig, Tressert, also Fiorucci. His thesis is really nice because it gives you like a motivation for these coordinates and all the reference therein. In the notes, the actualized version of the notes, you can see more reference there. And then we have all this term that contains the rotation functions, okay? And okay, this is kind of the main thing that one have to take when studying Bondi gauge, that we have the du square, du dr, and then the mixed terms that convey all the angular momentum information. In Minkowski, for example, is just obtained by saying that beta is equal to 0. And let's see. So beta is equal to 0, b is minus 2r, and this guy is 0, of course. And this metric here is, in Minkowski, this is just the round metric of the sphere times r squared. Once we have fixed the gauge, this is important because once we fix the gauge, we want to know if there is any residual gauge transformation left. That means that if there are any diffeomorphisms that are tangent to our solution manifold, which was fixed by this, and that remain like acting on the configuration space and giving us another solution. And it turns out that there are residual gauge transformations, and these are the ones. So we just impose that the RR components are still 0. The RA components are still 0 because we want to preserve this gauge. So when we act with some diffeomorphism, we want to preserve this. Therefore, the infinitesimal action of the diffeomorphism has to preserve this. And we also state that the derivative of the determinant of the AB part of the metric is a function only of u and the coordinate on the sphere. This is a technical part because we do not want to mix the determinant of this part of the metric with the luminosity coordinate, which is r. So that's the whole point of calling the coordinate luminosity coordinate. Now, once we impose these conditions, okay, we impose these conditions, we solve in terms of the functions b, beta, u, and what we obtain is what is the form of these diffeomorphism fields. Okay, so the generators of the diffeomorphism, first they start with some function f, which is dependent on u and xa, which that means that it doesn't depend on r. Then we have some function, which is a vector on the sphere. Remember that the coordinate a index coordinate on the sphere, plus some function which will be like subleading. And then we have the r component of the diffeomorphism, which is this one. So these are the residual gauge transformations that we have once we fix Bondi gauge. The next question that we have to do is ask ourselves, which boundary conditions are we imposing on our configuration space, such that once we have solutions with appropriate boundary conditions, we can restrict our configuration space to a solution space. Okay, so this is kind of the algorithm from the Lagrangian to the phase space. One has to impose a gauge, one has to resolve the residual gauge, and later one has to impose the boundary conditions. And the boundary conditions in gravity are kind of subtle because we have several options. One of the main options is assume that we, so let us suppose that we want stationary space types. So that means that in particular, we want Kerr solution to be part of this configuration space for the solution. So we kind of impose the follow for Kerr. That means that beta has to be subleading with respect to 1. B over R has to be subleading with respect to R. And the rotation function has to be subleading with respect to 1. So in that sense, these are kind of the most general boundary conditions that we can ask so that a simple solution such as care is contained in our configuration, in our solution space. And here we have the AB component of the metric, which will contain R squared QAB, which this function is a function of U and XA. Okay, so first of all, we are assuming that it could be anything on the scribe plus sector. So it could be a function of U, it could be a function of XA. And this object in here is also a function of U and XA. So this is kind of the most general boundary conditions that we can have. What one has to do now is write the R expansions and solve Einstein equations. We can solve Einstein equations not worrying about the compact sector, okay? Because in the region where the matter is, we do not care. We just care where the matter content is empty. So we are going to solve Einstein equations close to scribe plus, so that we are just solving Ricci equals 0. This is the equation that we are solving. Solving Ricci equals 0 is not a trivial task. So once we fix the R expansion that we are interested in, we say, okay, we solve Ricci equals 0 for the metric J mu nu. Okay, and you can see it in Barnich and Tressert paper. They did all the computations, the Christoffel symbols, the Ricci tensor, etc. Or you can do it also with Mathematica or any program nowadays. So once you solve, that will give you a number of conditions for the different components of the functions beta, B, U, A, and G. Okay, so I'm gonna show you just, for example, what happened. So beta, so if we solve, for example, the component RR of Ricci, so RR equal to Ricci, then beta will be a function of the CAB. So it will be something like 32 R squared CAB, okay, plus order 1 over R cube. Okay, so once we impose Ricci equals 0, we go component by component, and each component will give you some relations between the different functions, okay, the different coefficients of the functions. And well, we can do this, and we will have a solution space which will be consistent with Einstein equations and with our boundary conditions. Now, the thing here is that there are two elections that we can make when regarding to which is the form of QAB when we go to infinity. Okay, so let me write it below here.
Javier?
Yes.
Can I ask you something? So you're solving equations. What is the data? It's Q or C?
Exactly. So once we saw, I was going there. So when we solve these equations, Ricci equals 0, we'll have a set of equations, and we have to decide which is our initial data. Exactly. And the thing here is that we have two different approaches to which is the data. One possible approach, so data. One possible approach is to say QAB is always the round metric on the sphere. So we fix the metric at null infinity for AB, we fix it to be the round metric, and therefore say CAB is free data. So CAB as function of U and XA. Another possibility is to say that QAB, okay, QAB is not fixed, but the volume element is fixed to the round metric. And of course, this will be now part of the initial data, and CAB is free data. So these are two different choices regarding which is our initial data. What we are going to see is that if we choose this first condition, which is we are fixing the metric at null infinity and considering CAB as free data, we are going to obtain the BMS group of symmetries. And if we fix CAB as free data and also say that the metric is not fixed, but the volume element is fixed, then we are going to have what is called the generalized BMS group of symmetries. I don't know if that answers your question.
In fact, my question was regarding whether Q was arbitrary or Q was going to be gauge fixed, or where this is some freedom or not.
Okay, so in principle, you do not fix Q. So Q is a function of U and XA. What you can see when you solve these equations is that the derivative of U, okay, so the du QAB is 0. This is part of the equations of Einstein's equations. So
Okay,
you
so
can.
if this was going to be, I didn't know the equation, whether Q was going to be U dependent or not, because it seemed to me that it was pretty confusing for the leading term to be U dependent.
Oh, okay, yes. It is not dependent on U.
Okay,
Yes.
so it's going to be U independent.
U independent, but it can change from sphere to sphere, let's say, by a conformal factor, depending on let's say, so you have two different solutions, but they are related by a conformal factor.
So, sorry, what do you mean by a conformal factor? Because U doesn't have a conformal factor in front. Or does
No,
it?
but so two different solutions. So this Q could be the round metric, or it could also be round metric times some conformal factor.
Okay, I understand.
But the conformal factor does not depend on U. It's just
Great.
that you have a solution with Q round and another solution with a different Q, which is independent
No,
on
of
U,
course,
but
of course.
conformally
A
related.
deformed, some kind of deformed sphere at infinity.
Exactly.
So,
Yes.
I mean, just to have a naive intuition, the physical data is CAB, is the radiation coming out.
Yes, CAB, but you have like let's call a boundary, a corner data. Let's put it that way: a corner data that is which conformal family of the metric of the round metrics are you in?
Excellent. Thank you.
Great. So that's kind of the main point for generalizing BMS. So if you fix the scribe class to be the round metric, then the only data that you have is CAB, which is the shear of null geodesics going to scribe class. But if you leave free the conformal factor, then you have to specify another thing at one point in scribe class. And that point is spatial infinity, for example. And that specification comes with several problems. One of them is that now that you are allowing for a conformal factor to enter the game, you'll have certain variations that diverge when you go to spatial infinity, for example, and that is kind of the main point here. So just to review what is the BMS and GBMS, you have to remember this diffeomorphism that we have previously talked about, which were like a diffeomorphism in the U direction, then we have the transverse sphere directions, and of course chi-r. They are coming from U and transverse directions, so this will not play any role because, of course, if we go to scribe class, they will collapse to the U. So they are not important in this sense. And but what we want to do is to compute variations of the main parts of the metric. So for example, if we computing variations of data. So the action of a diffeomorphism on Q will be the Lie derivative with respect to B of QAB, let's call it AB, minus the divergence of C minus 2C QAB, okay? And what is B? So B is the guy that is sitting on the transverse directions, and C is some constant which comes from varying the conformal factor. So if we take that we are not varying the conformal factors, okay, so it's just fixing the metric at square plus, this guy will be 0. We are not taking it into account, and we will end up with the equation that is just the Lie derivative QAB minus this guy that is here, UAB, okay? And this variation of the metric, okay, if we take the round metric to be fixed at non-infinity, this will turn out to be 0, and therefore we are going to have what is called the conformal killing fields. Conformal killing fields satisfy this equation. Okay. Good. And one can also compute variations of CAB. And those are kind of some convoluted expressions, which we are not going to discuss any further. You can see it in the notes. What is important now is that these diffeomorphisms that we have defined, once we are sitting in this in both of these spaces, which is fixing Q or not fixing Q, but leaving the conformal parameter at play. So these diffeomorphisms form a closed algebra. So the diffeomorphisms are generated by main two functions. One is a function only depending in U along square plus, and the other one is a vector field on the sphere. And these are the expressions. So the diffeomorphism associated to the function, which is only depending in U, has this form. So these are subleading. And the diffeomorphism that depends on the vector on the sphere has this form. Plus U of, let's call it like this. Okay. And these are what called the generator of super translations. And these are the generators of super rotations. So the idea is that this algebra of diffeomorphisms can be translated into the charge algebra for the quantities that they generate. So each diffeomorphism generates a gauge transformation. That gauge transformation corresponds to some vectors on solution space, and those contain non-trivial charges associated with them. The algebra of those charges, the Poisson algebra, will be closed and will resemble the algebra between them. Okay, so that's kind of the main point. So just to make this more relating it with Lorentz symmetries and all that kind of algebraic things, you can see here that one can think this as the Cartan component of SL2R, because these are called abelian, is the abelian part of the SL2R. So this guy is the bicomponent of the vector field BA. Okay, so we have some bicomponent, although we are saying that the conformal factors are going to be fixed, we have some remanent coming from the vector field here. So the BMS algebra is contained in the Lorentz algebra is contained in the BMS, and we can say here like this. We have the isometries of Minkowski space 3, 1. This is equal to Lorentz with the semi-product with the translation. So this is Poincaré, this is Lorentz, and this is contained in the conformal Killing fields generated by this B. And now we have not only translations, a four-dimensional space of translation, but we have an infinite dimensional space of super translations. So you have to remember that Poincaré here has a four-dimensional, and this is a six-dimensional. And when we have the conformal Killing equation, which is this one in here, the conformal Killing fields on the sphere form a six-dimensional space. That is homeomorphic to this guy. So this is six-dimensional, but the super translation are any function, arbitrary function of U on square plus, and therefore it's an infinite dimension. So we have actually put Poincaré inside this bigger space, and this is what's called the BMS group, okay? So we have the super translations, infinite dimension, super rotations, all this guy. This is all good. So far, we are here fixing the metric, the round metric at infinity, and we are in that point. But what happens with the relaxation of, okay, we allow now not only to be the round metric, but it can be any metric, okay? Any metric conformally related to the round metric. This will turn out to be an extension of BMS by saying, instead of having the conformal Killing fields in this sector, we're going to have now, so this is BMS, and the extension GBMS will be, instead of taking any conformal Killing field, we are going to take all the diffeomorphisms on the sphere times the abelian subgroup of super translations. So the generalized BMS is considering, instead of saying, oh, we have the conformal Killing field, we have any diffeomorphism on the sphere, and we want to compute these charges. So how this extension works? Well, it is equivalent as to say we have any metric, but conformally related to the round metric on the sphere, okay? So we are going to see how this works. Any questions so far? Yes.
Since you want us to ask questions, we can ask Javier.
Exactly. Yes.
Will there be any problem on this generalized having conformal Killing vectors that probably will not be globally defined on the sphere?
Well, that's actually the first thing that Miguel and Alok, when they were proposing this generalization, encountered, because one natural generalization was done by Barnich and Tressert, and they say that instead of taking the conformal Killing fields, you take the conformal Killing fields modulo meromorphic function. So you can have poles on the sphere. So instead of this, you are going to have like some algebra which is diff time diff, some group, sorry. So the generalization by Barnich and Tressert was this one, where you have from conformal Killing fields, you go to conformal Killing fields allowing poles. And that's okay. You can do it, and you have a nice close subalgebra of things, and it's good. But the thing with, instead of allowing poles, allowing any possible diffeomorphism, is that this is consistent with the motivation of this soft theorems for graviton. So when you have a subleading soft graviton, what it ends up, the algebra ends up to be the diffeomorphisms instead of these conformal Killing fields. That's the motivation for choosing this over the conformal Killing fields. I don't know if
May I ask a question?
Yes, yes, of course.
If you allow these poles, what happened with the charges? Is there I mean, because you have to integrate, no, on the sphere probably. So are there they finite by including this, or
Well, I don't know. I think that, I mean, they are meromorphic. That means that you have finitely many poles, and probably the integrals will be written in terms of residues.
Okay.
But I don't know.
Okay.
Yeah.
Thank
you.
Javier.
Yes.
Yeah, so in this whole formulation, the point E0 and E plus are inside the manifold because this charge will be localized in those points, right?
E0,
Like the corners, yeah.
oh yeah, you mean this one here?
Yeah, that one and the one above. Those points are the one where the charge will be, the codimension 2 charge you are gonna calculate are gonna be there.
Exactly.
But those points are not inside the manifold, right?
Well, but when you take this
in the compactification, you have to add it or something like that. Or...
Exactly. You add those points. Now you are part of your space-time, but you can think it also as you have the Cauchy surface and you push it to infinity, and the finite limit will be infinite. It will not be finite.
Okay, but when you do that, the point E0, you have to do this trick about the how do you relate the Q minus with the Q plus in this point. This point is ill-defined, right?
When you take the limit, you'll have like to deal with the U going to minus infinity, and that will diverge.
Yeah.
So you have to, so either you do a renormalization of some sense for the Lagrangian, or you cook some symplectic form that is not divergent and gives you the correct charges. So yes, that's a problematic point, but you have to deal it because that point now belongs to your space because you are doing actual computations there.
Yeah. Okay, thank you.
Yes. So yes, those are the kind of the two things. You can do it, let's say by foot, constructing the things, or you can renormalize and see what happens after normalization. So both things have been done. Varnig, Tressert, and I think that I don't remember who else was in the group, but I think that Fiorucci also, they renormalized and they obtained the correct limit for charges. Miguel did it with a lock, and so, but they did it, building the symplectic form from by asking that the post-natural closes. So we can review this quickly.
Okay, thank you.
Yes.
Sorry, Javier, I don't know if you already said this before, but can you say a little word of why these charges are diverging on spatial infinity?
Yes, in spatial infinity, so when we want to compute the charges, so when we compute the charges here, we will have to integrate along some Cauchy surface. And on this Cauchy surface, we are going to have the symplectic potential, the T component of the symplectic potential. And the T component, I'm not going to write it for gravity, but the T component has, it goes like CAB, let's say. So it contains factors all over the place, but it has some CAB. And the main thing here is that these new variations, when you compute the variation of diffeomorphism of the sphere, when you compute it on, say, CAB, it doesn't preserve the U follow. So this guy will have a component. So in the GBMS picture, CAB will be of the form some function independent of U plus U and some function independent of U. So here, what we are doing is you take, for example, Minkowski spacetime or Schwarzschild spacetime, you vary with a diffeomorphism, with an arbitrary diffeomorphism, and it turns out that you have to add some linear in U components for the shear. And the meaning of that is that you no longer have the round sphere at scribe class. So since you have this deformed sphere, you have to take into account the deformation, and the deformation is linear in U.
And this U goes to infinity at I0, so this is blowing
Exact.
up.
Exact.
Okay, okay. And
Yes.
it's a consequence of the property of these killings you are applying.
Yes, it's just a consequence of the variation. When you compute the variation, how it appears, it's just a linear new thing.
Great.
So once you have this limit, so you have a divergence in U, you have this weird tensor, and you say, okay, so that means that our data will be the usual this function, it depends on U, but is subleading. So limits when U goes to minus infinity of this function is 0. So it doesn't depend on U, it follows really quickly. So your data now, when you want to construct this phase space, your data will be C hat AB, because it contains the shear, the usual shear, plus this tensor that is independent in U. And this tensor lives in the corner. And it's the responsible for the divergence. So if this tensor is 0, you are good to go. You don't have any divergences. If it is not 0, then you have divergence. You have to deal with it in some way. Okay.
But now you are leaving me another question. So what
Yes.
is the interpretation of this T? Is some what
Well,
kind of,
yes.
what is the interpretation?
I was going to get there. So
get later if I am taking you away of your
no, because actually you are taking me in the path of the of what I was going to say. So it's good. It's good. So just to recap, in case of we get lost on somebody. So the main thing here is that we have two different pictures for understanding gravity at null infinity. Those pictures are just the same thing, but with a little difference, which is in one case we fix the round metrics at null infinity, and on the other case we are changing it by a conformal factor. In one case we obtain BMS, in the other case we obtain the generalized BMS. Why? Because allowing for conformal changes in the metric introduce a divergence when you compute the symplectic potential, and that divergence is proportional to U. And you can actually show that the term proportional to U is independent of XA. So now you are left with the usual data from radiative space, but also with some weird data on the corner, which is responsible for the divergence. How can we understand this TAB? Lucky for us, there was this work by Guerrero who understood this TAB in terms of diffeomorphisms acting on the sphere. So what you can do is think the following thing. So start with a BMS metric, just the BMS. You have some radiative solution, and let's call it 0. So this is radiative. And now, since we want to allow for a change in a relaxation in the boundary conditions, our relaxation is that we are changing the conformal factor of the metric. So we want to study how a diffeomorphism acts finitely in this solution, base solution, let's call it. So what we do is act with a diffeomorphism, not call it psi, let's call it zeta, on this solution. So this is the dressing, let's call dressing of radiative data. So we dress the radiative data by some action of a diffeomorphism, and the idea is that this field in here, this zeta, will contain the information of the field T. So when we dress the radiative data, now our phase space will be consistent of zeta and JAB. So the radiative data will consist on metrics G0, and now our new radiative data containing this relaxation of the field will contain zeta and G0. So we are exchanging the relaxation of the boundary conditions by a new field that will act on the radiated vector. Okay, and this is not new. This is the Stuckelberg's trick. So Stuckelberg, what he did was, you have a Lagrangian, you want to know if it is invariant or not. You are some gauge parameter to the vector potential, let's say, and you do the computations. And if it remains invariant, then you have an invariant Lagrangian. This was done like, I think that 1938, like more than 80 years ago. But in this case, it helps us because what we can understand this new T as the action of a diffeomorphism acting on the radiated data, so we can parameterize that by a diffeomorphism. So the thing here is that what we are actually doing is that T AB is called the Gerov tensor of QAB with respect to the round metric. So if we have the round metric and we act finitely with a diffeomorphism and obtain QAB, there is a procedure by which we can construct this TAB in terms of the conformal factor relating them. So the thing is the following. There exists some vector field such that QAB, the exponential of the Lie derivative of the exponential of the Lie derivative with respect to that vector field is equal to QAB. So that's a finite diffeomorphism acting on the round metric, gives you the QAB. But also we know that since we are in 2 dimensions, this is equal to some conformal factor times the round sphere, and this is equal to this. And we can construct TAB. So I'm going to give you the expression for TAB if you want. Yeah. So if we have, so if this is the algebra, sorry. So if psi is the diffeomorphism associated to the vector field, we construct the change in the volume element, which of course has to be it has to remain invariant, but we have to construct this anyway. And we can do the following. We can explicitly say who's the conformal factor, and therefore T. So the conformal factor will be the logarithm of this change, because we want to remain it invariant, will be the logarithm of this change, and this TAB is given by this formula. So this TAB only depends on the conformal factor from going to the round metric to the new metric. Is that I don't know if there's any more question about this, or if you want to discuss any further.
Sorry, where your, let's say, freedom that you have by choosing your diffeomorphisms in S2 appear in this.
So the new freedom. So the new freedom appears in this tensor T. The new freedom appears in T, and this T can be explicitly written in terms of the diffeomorphism. So once you have the diffeomorphism, you can say, okay, T is equal to this thing. So you're parameterizing the new degree of freedom. You're parameterizing it by the diffeomorphism, this extra diffeomorphism that you have. Or you can call it like the conformal factor that is acting on the round metric.
Okay. Okay.
Yes.
Okay,
and that's a boundary term. Okay, so the new degree of freedom lives in the boundary. So lives in the spatial infinity, let's call it. So lives in this point. We can construct the phase space now by saying, okay, we have the possible metrics, and at each metric we are going to translate the radiated phase space via this transformation. So we have the possible diffeomorphisms on the sphere. We generate the possible metrics from the round metric by acting finitely with the diffeomorphisms, and now we have like an extension of the phase space by this new parametrization. And I have a nice picture. Let me show you. I think I have it somewhere. Okay, but I can write. So the picture is the following. So here we have the space of metrics such that the volume is equal. And here we have the round metric. Here we have the radiated phase space. And now we have to change different fibers with respect to the conformal change in the round metric. So here we have different spaces. So each one corresponding to a QAV. And the whole thing is what we are going to call the new phase space, the extended phase space. Okay. We can construct the symplectic form here, and the symplectic form will contain two terms. One term is the usual radiative term, but now extended to the whole diffeomorphism group. And the other term will contain exactly the boundary degrees of freedom. So it will be a boundary term for the symplectic form. So let me write the symplectic form. So let's make this better to copy it. So here we have the symplectic form. This is the hard part, or the integral along scribe plus. And then we have the boundary term, which will be this one, which is a little bit more ugly. So this is the radiative generalization to GBMS. And this will be the boundary contribution of the new degree of freedom. So if you see here, the boundary contribution that has the T and the Q. Of course, we can construct everything just in terms of Q, but it is nicer to have the T there, just to say that, okay, we have this nice Geroch tensor, so we should use it because it was written before. And this structure of having a boundary term for the symplectic form can be seen also in Young-Mills. So for example, if you go to the notes and see the Young-Mills part, the extension of Young-Mills, you will see again the same thing. You will have the radiated part generalized to the new free fields, because now you are allowing for extra boundary conditions, plus some corner term. And the corner term will contain the degree of freedom which lives in the corner. And now that degree of freedom is parameterized by this field which acts on the radiatives, and radiative fields acts as a finite transformation. So in the case of gravity, we see that if you have G0, then you extend the phase space by introducing the finite action by some diffeomorphism that lives in the sphere. In Young-Mills, it is interesting because you have your vector potential, which will be the finite action of some gauge transformation. So here you have the usual transformation. Here, I'm not writing the i's, we can absorb them in the A, but schematically what you have is a new field now, which is psi, which will parameterize together with the A mu, will parameterize the new extended phase space. And that is, again, Stuckelberg trick. You parameterize your initial radiative phase space with A, the fall-off, the radiated fall-off, and now once you relax the boundary conditions, you create this psi, which will contain the information by which you can relax the boundary conditions, and you act finitely with that guy. So now you're extending the phase space, actually. So now the phase space will be the possible psi's and the radiative rate. And this is the extended one. So what does it mean? Okay, first you have to be clear about how much the boundary conditions are relaxed. Okay, because you can go order R squared, order R to the power of N. You have to be clear, and therefore you have to do a consistent cutoff for this expansion. In the case of gravity, it doesn't happen because the variation is only order 1 in terms of R. So when you go to when R goes to infinity, then it doesn't have any problem. But these variations in Young-Mills, they already at subleading order, they have some divergences in R that you have to leave. Okay, you have to do some cutoff to avoid those divergences. So that's kind of the main take from today, that you can expand the phase spaces by taking these extra fields that live in the corner, generate the finite transformation, and then you expand your phase space. Okay, I don't know if I have any more time. I think that I have 5 minutes for questions.
Javi?
Yes, you still have 10 minutes for questions.
Okay, great.
5.
Yeah, we can. Yes, Facundo, I think that was.
Yes.
Yes.
And you can construct charges with this. What about them? Because in general, we say that the formalism are redundancies, for
Yes.
example.
Yeah.
Or, for example, take the electromagnetism case. The gauge transformations are redundancies. And with this formalism, you can construct charges associated
Exactly.
with these transformations.
Yes.
And in what sense, maybe this is a silly question,
No,
they
no,
are
not at all.
they are physical. In what sense they are physical charges?
That's the main thing. So that's when we are dealing with this stuff, the words suddenly start to lose meaning, because we are saying large gauge transformations, which is kind of we are saying that it's a gauge transformation, but it's large because it reaches infinity and it changes the solution. So it's kind of an oxymoron, because changing the solution with gauge transformations doesn't make sense. But it makes sense in the moment that you understand that when you go to Scribe Plus and you take finite limits at Scribe Plus, actually what you're doing is Scribe Plus now is part of your space. Okay, so it's actually a boundary in probably a bigger space. So if you say, for example, if you take let's take some null surface here, so N, and we have some corner, and we have the Cauchy surface sigma, and the corner is C. So let us assume, so this was done 3 years ago by Luca Ciambelli, Robert Lee, and later by Laurent Friedel. So what they did was, okay, this is a finite null hypersurface. It is in bulk. This C is the corner. So which are the symmetries? Which are the symmetries that preserve C? In the sense that which are from all the diffeomorphisms, which are the ones that preserve C? And what you obtain is what is known as the universal corner algebra. And the universal corner algebra, something like this, or universal extended algebra, I don't remember exactly the words, but I can look for it and then add in the notes. So the universal coordinate extended algebra, what it contains is, for example, dr, it does not contain any dr because dr will move the sphere. Okay, and it contains boosts, some of the boosts, and it contains diffeomorphisms of the sphere. So in that sense, what they show is that this universal coordinate algebra, when you exponentiate it, you will contain the diffeomorphism of S2 times the scalings, and this will have times some R squared, because the R squared parameters are squared to infinity. These are all the possible functions that can move the corner, can move, sorry, the null geodesics in here and in here. But if you push this sorry, and these are diffeomorphisms, but they have a non-trivial action on the boundary. So you can actually compute the charges for this diffeomorphism because they do not vanish on the boundary. Now, you can push this to infinity. So you can actually take C, push it all the way to spatial infinity. This N will now go to straight plus, and you will end up having diff F2 times the bile part times R infinity. Now, the dr direction, you don't have it anymore because we are in scribe plus. And this is exactly what we have. Well, we actually have a diagonal part of this product, but this is what these charges are all about. So when you consider diffeomorphisms, they are gauge, but you have to make sure that you are in the hypothesis for a gauge transformation. So, for example, it vanishes in the boundary. So if it doesn't vanish in the boundary, then it is not gauge because it will contain some non-trivial charge associated with it.
Yeah, I understand.
Yes. So this push into scribe plus is the thing that we are going to see tomorrow.
What we usually call gauge transformations is small.
Local, yes, local.
Transformations that do not reach at the boundary.
Exactly.
When we are talking about electromagnetism and
so when you solve in electromagnetism, when you solve the Laplace equation for the harmonic gauge, usually they say you, okay, constant and linear functions are not accepted because they will change the form of the field. So.
Oh yeah, you are in that hypothesis.
Exactly. Yeah, we are considering the definition of yesterday. So if we use the definition of local symmetry given by Lee and Wald, the usual definition, these charges should be zero because they vanish at non-infinity. But the main thing that we are doing is they do not vanish. So they contain non-trivial charges. Yes.
Yeah. Thank you.
Okay. Do we have more questions?
There. So summing up all this that you were explaining is that the large gauge transformations, what they must not touch is the corner. This is the codimension 2 surface, right?
I mean, the thing is, when they touch the corner, then you will have new degrees of freedom.
Okay.
And these new degrees of freedom, you can parameterize them by extending the phase space via this stupid trick.
Yeah. Additionally, one related question is the following. For example, you can have a massless scalar or a gauged massless scalar, and in one case, the charge, the U1 charge is codimension 1, and in the gauge one is codimension 2.
Yes.
And it's the same phase space because if you do the path integral is the same path integral. How do you relate one to the other? Because you don't have a codimension 2 charges in the scalar in massless scalars.
Yes. So in this case, I mean the let's say the layman approach is to write the equations of motion, and what you will have is some relation between the du derivatives of the fields with the fields, so the massless scalar field. So these relations you can actually integrate it by parts, and go from a integral in stripe plus to a corner part. So you have like the whole thing along stripe plus. One part of that thing you can integrate by parts, and you will have like two contributions regarding the borders. So the boundaries, sorry, of the stripe plus. I don't know if that is your question.
Yeah, this answers a lot. Would you have a reference for this?
There are that thing is scattered all over the place. I think that one place to start is Miguel Campiglia and Alok Slada first paper in electromagnetism, but there is also one paper by Laurent Friedel and Mark Giller, where and Daniel Pranzetti, 2018, I think. They study this electromagnetism and the extension of the corner degrees of freedom. So what they do is, okay, we have these electromagnetism charges. How do they relate with the corner, regarding that you have also some extra degrees of freedom, radiative degrees of freedom. So they do the example with some charged particle. Yeah.
Okay, thank you.
Yeah. I can send it to you later.
Okay, thank you. Very useful.
Sorry, in this case, just to be sure, the charge will not be integrable, right?
Well, that's
because of the radiation, or I'm quite confused.
That's no, that's in many cases that's the case. So when you have BMS, for example, the charges they contain non-integrable terms. Okay, by suitable boundary conditions in U. So when you approach minus infinity, you can kill the non-integrabilities by saying, okay, this vanishes, and so you can integrate
in the corner, let's say.
In the corner. Yeah, you can make it integrable in the corner. But when you consider this extension by the Stuckler field, you can actually show that there is a procedure by which you obtain integrable charges at the corner. So it's a formalization. So there's a formalization by which you obtain integrable charges. Yes.
In some sense, exact without taking the limit, or
well, for any corner at a finite distance, and then you can push it. But it's in the corner. Yes.
In the corner. Okay.
In the corner.
Okay. We are 5 minutes of schedule, so let's thank Javier about his very nice lecture.
Thank you, everybody, for the attention, and see you tomorrow.
And now we have a 10-minute break. 10 minutes, no?
Maybe we can do it 5. So
okay, 5 minutes break with film noir music, and we're back in 5 minutes.
Okay.